All right, so it's a way of introducing the next 4 chapters. We start out with a scenario here of 2 objects heading towards each other. They're going to collide, and so they're all within 1 dimension right here. So this is the dotted line where they'll actually meet. So a moment later, they're that close. A moment later, they hit. And then at this point, they will shift, move together, combine, and then they will separate, going in opposite directions. So, while they are touching each other, there are 3 things that are the same for both objects, 3 quantities that are the same for both objects. What are those 3 quantities?
Would the velocity be the same?
No, because they start out going in opposite directions when they first hit. There's going to be a transition before they have at least the same velocity in this from here to here, and then at that point they separate again, so velocity is not the same. Is that a sense of danger?
So there's 3 things that are the same when they hit.
3 quantities that are the same while they are touching.
Normal force between off of this, or away from each box.
Okay, so what's the same?
The magnitude.
All right, so the magnitude of the force. So right now, whatever forces they're exerting on each other, we'll just deal with that. So we got the magnitude of the 2 forces. So the force that exerted on A from B is equal to the force exerted on B from A. We'll make it more formal in a moment. This takes care of the forces. We don't have to bring up any more forces. And I will say that the one that most groups have the hardest time with is the one that is the most obvious. There are only a limited number of quantities we've dealt with, so.
Are they the same mass?
No, mass would not be the same.
So that means the acceleration would be
Correct. Mass may or may not be the same,
but not necessarily.
not necessarily.
So there's no other forces.
Pardon?
There's no other forces, right?
We don't have to worry. Let this cover all the forces, whatever forces are involved.
Okay.
In this particular scenario, it'd be normal force, but I mean, if there's some slight sliding against each other when they hit, there'd be some friction. There's a gravitational force because they're 2 masses, so we'll just bundle all those up. Just the magnitude of the 2 forces are the same.
Energy.
No, that's premature because we haven't studied energy officially.
Oh.
But you know what? Energy's not going to be the same for both.
Well. Not even kinetic energy.
No,
Because they're not moving the same speed necessarily.
they have different masses also.
Oh.
Even if they were moving the same speed, kinetic energy would not be the same.
So you're asking at the point when they touch.
From while they are touching. So in my incredible series of drawings here, somewhere in this range right here.
Speed,
Sorry?
the speed,
No, velocities aren't the same speed. Well, I guess speeds could if velocity's not, but no. Not speed. Looks like an electroscope right now.
because like, you know, when they're touching, they're both gonna be at zero for a little bit, so.
Not necessarily, since, not necessarily at the same time. The way I've drawn it right here, since it moves that way, A would have to go through zero at this point, B would have to go through zero at this point. Think about movement of the centers of each of them.
There,
Who's
so it shifts this way, right?
Yep.
So it could go negative.
You're making an assumption about which direction is positive, but
The direction's the same, I guess.
So it moved.
You can expand on
I
that.
think they moved left and then,
yeah.
how's that work? Is it,
For the sake of this, assume it, in terms of picturing it, if I was using,
that's it, I guess they're switching.
so they're cruising along towards each other like this, they hit, and so this is still moving that way, this is moving that way, there's going to, let's see. Yeah, it depends upon basically the relative masses of them. They hit and then separate, whatever's gonna push them apart. Yeah, so whatever's gonna push them apart
So it's not.
it's not instantaneous.
Yeah.
So Osama sort of talked about the fact that they're both going that way.
Yeah, so it's the same.
We can be more specific than the same direction.
Same.
Setting the psychic waves on. What quantity deals with they both moved in the same direction? It's not velocity, we've covered that one already.
The displacement's the same.
B is moving from here to here, A is moving from here to here. My drawing's a little bit off, but displacement. So the displacement of A, is the same as the displacement of B. And then the most obvious one. And here's one of my two most obscure clues. It's the name of a Bobby Sherman song. I generally get that same look from all my classes where I mentioned Bobby Sherman, except for one. I did have a student, an older student, who had actually been to a Bobby Sherman concert. His sister was a fan, he claims.
What's the next clue?
Oh, my other obscure clue, will show up in a couple of weeks. Just as a teaser, when someone suddenly buys you flowers, that's called. That's the other obscure clue, but it doesn't really apply here at the moment. I don't know why I can't remember it. It might be the song, name of a Pink Floyd song too.
It's not the gravitational force, is it?
Force is already taken care of.
Oh, right. But wouldn't that be the same?
It would be, but, so that's why I just kept it generic. I didn't specify. You said normal force before. I just let this represent the force or total force.
Position,
Pardon?
position.
Position's not gonna be the same. Typically with an object, when you're talking about position, you're talking about the center of mass of it, and center of mass definitely not the same. I am gonna put that one over here. Yeah, I don't know why this one is really hard for most groups to come up with, other than it's so obvious people don't think about it.
The time.
Yes. They touch each other for the same amount of time. Time, the Bobby Sherman song. It's a uplifting one. Time, we all die sometime, no matter who you are or what you do. We all gotta go. We all gotta die sometime. You know, upbeat. It's that early 70s thing. All right, so what does this have to do with the next 4 chapters? Well, if I combine this idea of force and displacement, we end up with the concepts of work and energy. If I combine the idea of force and time, we get the idea of momentum and impulse. In this particular textbook that we're using, this is the next 2 chapters, and this is the 2 chapters after that. What we're going to do is take the same stuff that we have been doing, except we're going to look at it different ways, because sometimes it's not particularly convenient to use Newton's laws. So if I have 2 things crashing into each other, to be able to apply Newton's laws, we have to know something about how the force is being applied over time. And from that, we could find the acceleration, which would not be constant, and it can be a real mess. When oftentimes we don't really care about what's happening during the interaction, we just care about what's going to happen afterwards. And so that's where these come into play. Some physicists consider energy to be the, sort of that fundamental of all of physics as opposed to forces, but when we'll derive our formulas for energy, we'll be using forces. So that's why I consider force more fundamental. The advantage of this, so the plus side of using energy, is they are scalars. The downside of it is that they are scalars. Because we're going to lose some information. When we start dealing with scalars, we lose information about direction. Momentum and impulse, it has the advantage of being vectors, and it has the disadvantage of yes. The math here is more complex than the math there. So let's start out with this force. I do want to bring the vector, the directional aspect into it at the moment. This is the force on A from B. And that's gonna be equal to mass times acceleration. And that's the acceleration of A and the mass of A. Because I know where we're heading, I'm gonna multiply both sides by the displacement that it undergoes while this force is being applied. So I have force. Actually, I'm just gonna do the non-calculus derivation of it. We don't need to do that. So what I do, well, actually, I'm gonna keep this for now. The force acting on A from B times the displacement of A. That is known as work. In order for work to happen, there has to be a force applied and there has to be some displacement. So right now, I'm doing no work at all on the door because I'm not applying a force. I'm not doing any work on the blue circle because I'm not displacing it at all. So we have to have force and displacement. Because force is not necessarily constant, we can have a change in work is equal to, not yet. That force, we'll just force on A dot dx. So if I really want to know what the work is, instead of doing the sort of the macroscopic force is constant routine, we can look at it with a changing force. So if I integrate both sides, my work is going to be equal to the integral of f dot dx. dr, ds, whatever letter you're using. I know force is mass times acceleration, so this becomes the integral of mass times acceleration dot, it is a dot product, dx. And what is acceleration? The calculus definition of acceleration.
Change in velocity over time.
Oh, yeah. So that's mass, calculus version,
Change in velocity over time.
not change. Change is sort of macroscopic. Did you say it? I missed it. Yes, I'm not going to repeat myself. dv dt. Not dx. Now dt here is a scalar, this change in time. It's infinitesimally small, but what I can easily move it, masses I can bring out, dt I can bring over. And so what I end up with is the integral mass times dv dot dx dt. And what is dx dt?
Velocity.
So I now have m integral of v dot dv. All right. I am going to put hand wave there. And I'm going to take this from some initial velocity. I won't hand wave that. There's some final velocity. Anyway, what's the integral of v dv? Or antiderivative? That actually, this one integral should work. You prefer, what's the integral of x dx?
1/2 x squared.
Yeah. So if I have an exponent of 1 here, you add 1 to it,
Plus.
and then divide by it. So, or 1/2 x squared.
Is there a plus c?
There would be here, there would be a plus c. Here, I made it a definite integral.
Oh, right.
So what I end up with here is that the work done is equal to 1/2 times the mass times VF squared minus VI squared, which we can then make it 1/2 M VF squared minus 1/2 M VI squared. Now that 1/2 MV squared pops up enough that they said, you know what, let's just give it a name. Let's just give it a letter. How about K? We're not using capital K for anything. That would be K final minus K initial. Where do we just define K to be 1/2 MV squared? And if I got final minus initial, how can we shorten that?
Average K.
Not average. Average would plus and divide by 2.
Change delta,
Say it again, Benjamin?
change in K.
Change in K. Now recognize this work here is the work based upon this force, which we said is equal to MA, which means this is a total force. If F equals MA, that is the total force acting on the object. So this would be the total work. So we have this relationship here based upon this definition and the definition of work, that the total work is equal to the change in K. This, I don't assign the names, this is the name that's been given to it. This is known as the work energy theorem. Frankly, I don't think it should be called a theorem, but they did not ask me. This K, obviously, since I'm now calling a work energy theorem, there's got to be energy in there somewhere. This is kinetic energy. It is the formula for kinetic energy. It is the one formula I expect you to know cold. 30 years from now,